Warm greetings from the Department of Electronics and Communication Engineering, Rajiv Institute of Technology, Hassan. We welcome you all to the sixth day of Virtual Faculty Development Program on Advances in Signal Processing and Wireless Communication in association with IETE Mysore Center. Today, we are having with us Dr. Akhilesh S. Tyagaturu. He is currently working as a senior software engineer with the Programmable Solutions Group, Intel Corporation, Chandler, Arizona, USA, and an adjunct faculty with the School of Electrical, Computer, and Energy Engineering at Arizona State University. Akhilesh S. Tyagaturu has received the PhD degree in Electrical Engineering from Arizona State University, USA in 2017. He serves as a reviewer for various journals, including the IEEE Communication Surveys and Tutorials, the IEEE Transactions on Network and Service Management and Optical Fiber Technology. He has served as Technical Program Committee member and as session chair for various conferences, including IEEE International Conference on Communications. He has 489 citations to his account with Scopus H indexing of 10 and I10 indexing of 10. Sir, thank you very much for being associated with this FDP.
Hello everyone. I'm very happy that I got an opportunity to participate in this faculty development program. So my name is Akhilesh Tyagaturu. I currently work as a software engineer at Intel. I work for a group called Programmable Solutions Group, and so they develop FPGAs and accelerators, ASIC accelerators, to primarily assist CPU for routine functions like cryptography, encryption, compression, um, and specialized functions for these network function accelerations. So we will define all these terms briefly in this presentation. So with the topic that I have chosen to discuss with you all today is software-defined networks and softwareization of network functions. I'll touch upon the very fundamentals of these topics, which not to go in depth, very in depth that you will lose track of it, but to ensure that you get the main ideas and the general overview of the field in the latest that it can be, so you can use it in your own research or trying to find some of the interesting problems that might exist in this area. Um, okay, so that was a little bit about myself. The presentation of this topic would span approximately 15 minutes. It's just 10 minutes question and Q&A. Probably you can make a note of the emails, make a note of all the questions and email it to me, and I'll try to answer it to you. So the general topic is the topics that we will be discussing are what is an SDN? SDN corresponds to software defined networks, and we will also define what is a network function and what does it mean when we say softwareization of network functions, and the use cases of all of these. Where do we apply all of these concepts? What do they truly mean? And we will see how these technologies and can be applied to build a flexible and optimized latency um, that it brings when we have a packet transactions from one device to another device or one end to another end. And we will conclude with some interesting questions that might arise, which could be discussed on its own uh, to find out some of the research problems. So this is just a generic slide that I put up every time when I get a chance to talk to my colleagues and friends. So what this would say is that all of us will be seeing Orion constellations, and I think it's pretty visible in the winter. Um, so the Orion is a Greek mythology. Is He is a son of a god, which is he the key point here is that he becomes a blind, um, and as a because of his mischief, someone takes his eyes off, and then while stepping on uh, being blind, he walks into some other kingdom, and he meets a king, and the king he begs for help, and the king would grant him a servant named Sedalian, and he will say that Sedalian will be the eyes of the Orion, and he can navigate to the end where the sun, I mean SUN, where the sun will be able to pardon him and grant him eyes. So the whole moral of the story is the Sedalian is a tiny, short, young man, and Orion is a giant, blind man. But they go together. So Sedalian will be sitting on the shoulders of Orion, and he would navigate it. So Isaac Newton brought this up as a reference, saying that we are all a part of the story where we are all Sedalian, where we get to stand on the shoulders of someone else to see. So what we get to see. So it's all our achievements, all our efforts are definitely attributed to someone else whom we are standing upon. So with that, whatever I have learned is definitely attributed to someone else who has gracefully helped me learn that or share the knowledge, um, and help me believe in what what the true effort should be to gain knowledge. So with that, these are some of the presentations, like conference presentations, patents, and the regular journal articles that most of the discussions in this um, discussions are related to. So we're going to pick and choose the topics, all the figures that has been used in this presentation are adapted or actually taken directly from these articles. So if you were to know more about some of the topics that we would discuss, I have added as a reference on each of the slides. You can go and find out more details on the topic. So with that, I also involve in a lot of reviews. So I get to see what is the current latest research activity. And so with this, I will be able to bring in some of the latest information in this area. Um, More importantly, some of the challenges where you could use it to find your own research problems and contribute in the field. So we are beginning with the journey with a brief introduction on networking. So what networking generally mean is that packet transaction from one system to another system through various links and nodes and gateways. Plenty of no systems that process these packets in between before they actually reach another end device. So in general, some of the traditional terms that are important term uh, is to know the understanding of access network. So access network exists between the device and the core network. So core network is would be data centers and central office, let's say BSNL, for instance, or T-Mobile carrier network. And the access network are the ones which links or connects the devices. For instance, wireless LAN is a wireless access network. Your Wi-Fi is a wireless access network. And cellular network is a wireless access network. So the base stations or the wireless access Wi-Fi access points are actually the last hop accessing. So the phenomenon of devices being able to access the core network which is present in the carrier network, in the carrier infrastructure, is actually the access network. That's very key important term because we will be referring to this access network in where in multiple locations, and it's very important to understand what does core network mean, access network mean, and of course how what's their role in connecting a device to to an internet, and also enable packet transaction from one end to another end. Um, s- with this, we can directly jump into the concept of software-defined networking. Software-defined networking is a paradigm. So when I say paradigm, it's a way of doing things. It may be riding a bicycle. So the one may ride, one may get onto the bike, left hand first, or another one with the right hand first. So it's a way of doing things, and software defined networking is a paradigm and a different way of doing the networking. So whenever we refer to the term called networking, it actually precisely means that something to do with the packets. And that something can be dropping it, forwarding it, manipulating it, encapsulating it, or forwarding it to some other completely total analytics node. So it can be a multitude of operations on a packet. So to get a contrast of what is software defined networking, we would have to go back like roughly 10 years ago, and how the traditional networking used to operate. And mostly when we have learned the networking, it would have been the traditional way of networking, which would be, we bring in a router or a switch, and when we set it up, we have to go use admin privileges, configure them, and deploy them at first. And then once you enable the infrastructure and all these routers being interconnected here, if you bring the setup, and if when you switch it on, what they would do is basically they would find out who their neighbors are, how far they are, and how much cost would it take for each of this router to reach each other router as a part of destination. So that's called learning mechanism, and that's like L2 learning, routing table generation, forwarding table generation. For instance, path, open shortest path first, Dijkstra's algorithm. So what would happen is when we switch on this infrastructure, a little autonomous agents on each of these routers and switches would go and flood the network and try to learn the network infrastructure distributively. There is a problem with associated with this. What people realized is as the network grows, the total number of the amount of complexity that goes into the network building will increase, and since the mesh it increases in n square order. So that's not a good thing. One, and then we would, as engineers, we would want to play with it. We would want to change it. We want to reconfigure it at our wish, and we would want to do it in a software manner. So what I mean by that is we ideally want to take over the control of the network, and we should be able to program it. Like we should be able to send instruction to each of these routers to be able to say statically upload all the routing tables. So that concept of generalizing a network operation through a centralized node. So what would happen is you take out all the independent logic entities and centralize them in the controller. You what would happen is like we will take out all the uh, autonomous agents that were doing the learning, all the intelligence that would have existed on that router. We want to take it out and place it in a centralized location called controller. So that's a very important concept because now you want to make the switch as dumb as possible. So switches have no intelligence in SDN. What they would do is they would wait on the controller to to send the instructions for them. So so when we switch on the SDN switch, what would happen is it just waits. It just waits for instruction, someone else to tell the SDN switch what to do, and the controller having the global view of the entire network would send in rules and policies that needs to be applied on these switches in order to operate the entire network. So now when we look at the generalized abstraction of what's happening in the traditional approach, the networking was one big fat layer, which is like it just exists in atomic way, in a total entirety. You couldn't have broken it into different layers. But in SDN, what happens is now you have a dumb infrastructure layer. The reason why I'm calling dumb is that they have no intelligence. It's almost like you take dead phones and trying to connect them. Basically, or actually live phones, but no, without SIM card. So it's like they don't have any information at all. You just brought some of these networking nodes and placed them and connected them via links. You know. And controller is now sending instructions. So imagine you have eSIM card on your phone where network would send you all the instruction onto the device and let it know how it should perform. So similarly, that's the intelligent part is now called the controller layer. The reason why we call it as a layer is because there could exist multiple components in the control layer. But we want to keep in mind the for every SDN switch, the control layer or control element is logically centralized. What does it mean is, for instance, let's say you would want to access google.com. So for me, for you, and for anybody else who is accessing google.com would look as a logically centralized location, which means that we would assume that we are accessing the same server, but internally it might get load balanced across multiple nodes. So that's the way even each of these layers are being used, in the sense control element can be multiple, but logically for each of these switches would look as a single entity. And as for the application layer, it's as simple as the Google Play Store. So for instance, let's say you want to install a L2 forwarding mechanism, which means I just want to set up a simple switching LAN switching uh, L2 layer switching nodes. It's called a switch. The term that I was trying to think about was switch, not the router. Router would operate in a L3, which is IP layer. So L1 is physical, L2 is MAC, and L3 is IP. So when we say L2, which means that it only looks at the MAC frames and it forwards the MAC frames. So if I were to build that infrastructure, I the simple application that one could envision, and also which exists today in several marketplaces, is that it could be as simple as having a Google Play Store and you download the app on it. So similarly, if you want any network application that to be realized, we would just uh, we would just download the um, we would just download the application and try to install the whole thing. The controller will take care of installation. So there are it's SDN has been widely adopted. Intel has several products which supports SDN. I think in most of the latest infrastructures, SDN is becoming ubiquitous, which means it exists today, and it's where it's a it's a paradigm, which means that it's a way of doing working. So it also exists as a part of legacy infrastructures. So which says it can be backward compatible, which means let's say your controller is off. That mean which that is almost like, let's say if a king is gone in a kingdom, what would the each of these individual ministers do. So uh, they would have to assume their own roles and keep on going, right? So similarly, if the controller dies, then the SDN switches would fall back to the traditional mode of operations, where they try to go and learn who are their neighbors and how they need to forward the packets. So that's the way that SDN coexists with the traditional ones. Here is a simple layering concepts. You know, so so if we look at the very lowest layer, we have represented nodes, the network nodes. You know, when we say network element or network node, forwarding node, these are the hardware SDN switches. So when if we were to go and buy off the shelf hardware equipment for these, if we can go and say that I want to buy SDN switch, or SDN gateways, and that is the yellow blocks at the bottom layer are indicating the hardware devices which supports SDN, and that's the infrastructure layer. And typically, what happens is the actual underlying hardware is messy. For instance, if you look at the platform of your laptop or a desktop, it's the hardware is so messy. You have so much components. You have two types of memories, disks, a lot of PCI devices. So managing each one of them is very hard process manually. So the OS is by default enabling abstraction layer. So what it would do is it would take care of all the mapping and arranging of these address spaces, taking care of virtualization. So there would be an abstraction layer for to take care of messy items, and that's typically enabled through hypervisors. So same thing exists on these network elements. You What happens is, the hypervisor is also a centralized entity which is doing all the messy work of underlying hardware elements, and it communicates with the controller. So what would happen is the virtualization layer would abstract the bottom. Let's say you would want to access um, a memory, and it would be what would OS do is it would virtualize, and for applications we would pass in the virtual memory, because each application need not have to worry about swapping, paging, resolving page fault, and all of it, right? So similarly, hypervisor is specialized to to abstract all these hardware components and present it to controller. So one thing that can be understood in in this context is, when from our perspective, when we look at the top down approach, let's imagine that we are sitting on top of the hypervisor, and you look towards bottom. How it would look is basically you would be seeing entirely new versions of hardware, so not the infrastructure itself, but it can be entirely new thing. And from the bottom view, from the network element view, when we look at the top, the hypervisor would look as a controller itself. So what's happening is the hypervisor is just like a transparent mirror. It's for controller. The hypervisor acts like a SDN switch, and for network element, the hypervisor acts like a controller. So it's from the top down and bottom up. It's just trying to abstract each overview. I mean, each point of um, reference. And then the controller itself, as I said, referring to Google data centers, the SDN controller itself is a multi-level approach, where we will have a local controller and a root controller. So this is something similar to uh, you know um, the local controller is taking to take care of the local aspects of very short geographical handful of devices, whereas the root controller would would be taking care of managing the local controllers. So it's hierarchical view where we get to abstract at each layers and try to minimize as we go higher and higher layer. As the infrastructure layer, which is the bottom, increases, we get to abstract however we want and then try to deploy applications at a scale we want, and also for flexibility, isolation, resource sharing, all of those benefits can be adopted. And the right one, the optical node is just an indication of how the optical um, mm, in similarity to the actual network elements, which are non-optical. We have just referred it how optical nodes would look like. That's not a very specific item that we should be focusing on this presentation. And then the another concept that is very important to understand is you need to understand the terms and the interfaces. So what is the interface? Interface is just a logical extension of communicating link, which means you have, let's say, application layer, application agent, and then you have a controller layer where you have a controller, and how these two communicate. These two communicate with an interface, and up and from the perspective of control layer, we could say, I mean, we will be referring the connection that goes towards application layer as northbound interface, and the connection that goes to south is called the southbound interface. I mean, that's why infrastructure is called southbound interface. And if there could be multiple SDN domains that exist in the deployments, and controllers of each of these domains can talk to themselves, and the westbound interface connects two SDN independent SDN domains, and eastbound interface connects legacy traditional non-SDN network with an SDN network. So you have four interfaces: north, south, east, and west. So what is an interface? Give an example. If you were to ask me, give us an example of these interfaces. A simple HTTPS connection itself is an interface. So it's just a stateful end-to-end logical interface to exchange information. That's it. But when we if there exists a common interface across everything, if everything is HTTPS, it's very hard to uh, infer to which of these HTTPS connections that we are referring to. So that's why this nomenclature exists. So if somebody says northbound interface, they are referring the communication between controller and the application layer. So just to reiterate, the application layer means the actual applications, like your Word, MS Word, presentation, OneNote, Outlook, Chrome. So similarly, all of these, I mean, I referred it to applications on a laptop, but in the network domain, these applications refer to some of the network functions. Let's say switching. Switching is also as an application. Routing is an application. Firewall is an application. Load balancer is an application. So all the code that implements the function are being categorized as an application layer. And these the place where all these programming are broken down into little functions, where the instructions needs to be applied on the infrastructure layer, which is like network node, networking elements, nodes, switches, SDN switches, all of it. So controller layer is similar to your operating systems, or the compiler, which compiles and executes on the CPU. So controller layer is the um, main intelligence agent that exists in the SDN. So four interfaces: north, south, east, west, each of them referring to the connections in relation to controller. Right? So now we want to understand the domain. What does SDN domain mean? And layer, when we say the um, um, when we say layer of operations of SDN, so SDN can operate at different layers. So here you would see four different aspects. One is the IP layer, and then we have a WDM layer, which is like web division multiplexing. So that's a physical layer, right? So you can have independent SDN controllers in the sense, if you were to manage these optical links, you could have a SDN controller specific to this layer, and on top of it there is an IP layer, which is like IP packets would be running on top of the WDM switches, right? So obviously it's embedded inside, but logically there is IP packet going through, and you could what is we could start independently programming that IP, how these IP packets are handled within the WDM. So it's a it's an approach that that separates the layer, and each layer can be controlled independently by a controller, obviously independent controller. So there will be two controllers trying to there is a there, even though the left is saying SDN controller intra-domain, there is a separate controller. It could be separate controllers in each of these layer controlling on its own and then reporting back to the root controller. So what I meant is, what the very gist of it is, SDN can be applied to control the networking functions or applications. All the packet movement that is happening at different layers. So it's almost like, let's say you want to send a post from one person to another person. Uh, so there's a postal service, right? That you can control. The Department of Postal Service, which is trying to take control of it. And let's say you are in a university or a college, and there is an internal sorting facility, which they have their own control. So I mean, have their own policies, like packaging, having a uniform address, and all of it. So at each of these, postal office controller, and then university or a college kind of postal service. So these two are independent. They can be operated, controlled independently. Uh, we can program them independently, and each one of them have their own controller, and then they can report back. That's what I explained was is one domain, and that can be of multiple domains. So there can be, let's say the university is with you and they have their own controllers to operate, and then the autonomous institutions, they have their own way to operate. So all of these would eventually merge and report to a single controller, like a vice chancellor of the university, or the governor who is on top of the vice chancellor. So the goal here is that regardless of the heterogeneity that exists in the system, you can homogenize by having the local controllers, like intra-domain controllers, and then there is a separate inter-domain controller which merges everything at a very high superficial layer, and then have a common management of all the nodes, um, and all the nodes and links and all of system establishments, packet movement, all of the functions that comes along with the networking. So the next terminology, um, which which goes hand in hand, but it is not a new, or it's not a new technology. This is just this is what exists from the beginning or the inception of the networking. A network function. So we need to understand what is a network function. Network function is, the way that I would put it is any operation on a packet is a network function. So as long as you are trying to perform an action on a packet directly or indirectly, we could refer that as a network function. Examples of that are firewall, load balancing, um, packet drop, deep packet inspection, anything. So a network function now is a definition of of packet processing. That's it. So if you were to define a function, let's say you want to forward a packet, so you can write a program. Right? You can write a function. Uh, of course, a piecewise function or a big if else function. If this do that, if this do that. So we can define now what should be um, our packet processing function should be. So uh, that's the key thing that comes along with the with abstraction or the term of network function. So now we understand what is network function. So the next thing that to go for to look at is, can we program it? The meaning of programming is that somebody has to define it, right? So if SDN is now like a calculator, it does not. It's a compute now. It's a compute node. As long as we type it and we press an enter, it doesn't know what it has to do. So each switch in SDN framework doesn't know what to do. We have to program it. We have to type it. So the network function definition, execution of this gives a whole different paradigm to how these networks are operated. There exists a lot of programmable switches in the context of SDN, where controllers can go and program them as simple as writing an if else loops on a C program. We could compile and run as an application. So that's where this network function comes in. Can we define the network function, and uh, and can we program it? Can we change these FFX? Is a key aspect. And where to run this FFX? Right? The FFX will run on the forwarding elements, and we can refer to that as data plane. So another thing, if we were to discuss in SDN, the topic of SDN in this session, one of the key aspects that needs to be taken away is the definitions of control and data plane. Uh, in fact, the whole definition of SDN, the one way to put it is, SDN is a paradigm of a paradigm in the networking where control and data planes are separated, and and data plane is programmed by the control plane. So the meaning of it is that in the traditional network, control and data would exist on the same node. Now you separate the control data plane and you centralize it. That's the concept of SDN. So with all these concepts, we one should note is that we can program the switch. We can tell whatever it to do, and switches will run it. So the next concept is the softwareization of network function. So what happens is the calculator itself has been programmed, right? So it can accept only what a calculator defines, or are the buttons that we have access to press to. So what if I can define my own calculator, which is like I can write a code and I should be able to run it anywhere, or the most generic sense is general purpose compute. General purpose compute, GPC, refers to the CPUs, traditional CPUs. What is in our cell phones, what is in our tablets, laptops, servers. So simple one, Intel chips, Intel CPUs, x86, ARM CPUs, and AMD CPUs, both the CISC and RISC architectures, Tensilica, DSP, so all of any of it. So as long as we can program it and run it on a general purpose compute, we can softwareize this function, which means we no longer have to go and buy the specialized SDN hardware. We can program the Intel CPUs or ARM CPUs or Qualcomm CPUs. Snapdragon CPUs, Tensilica CPUs, and DSP, TI. So we can program all these CPUs to be running as a switch, running as a gateway, running as anything what we want. So the goal here is that softwareization is a very important concept where we get to run the network function, which is like any operation on the packet, on on any general purpose hardware. It could be laptop, servers, and mobile, even mobile phones tangentially. So that opens up a very big ecosystem of network deployments, which says that, for instance, um, we can develop any function of a network, and now we can move from one location to other location. It's just a software patch, so it's like virtual machine. So you create your desired network function as a virtual machine, and you propagate that across different nodes, and we get to, I know, propagate as well. You can duplicate, you can copy it, you can move it, you can do whatever you want. Now you have the flexibility of traditional applications. You can download and install, you can move it, you can copy it. So that's the benefit of having softwareization of networks, or soft networks function softwareization, which is to manage. SDN manages it, copy, move, forward, all of it. And the second one is the implementation, where there's a common CPU. You just go and install the software. It doesn't even tie to a particular hardware. For instance, to buy from HP, it has to be Dell, things like that. There is no restrictions. You can run it on any general purpose. You can find hands on. So one of the application would be, you develop a VM and you do a service migration. So that's there is something called follow me fog, and follow me general follow me concept, which means um, wherever you go, you can take your network, and that translates to VM migration. So move a VM from one location to another location, and you get to instantiate your network service at a different. So follow me concept is primarily to migrate the services which are physically, in terms of geographical placement, is let's say is learned, and the properties of that uh, service is migrated to a different geographical location through migration process, and that the whole migration is triggered by an entity where user is physically moving from one location to other location, and the service also moves along with the user. That's the follow me concept. And the next important topic that we should discuss is the general purpose compute. Whenever we refer to a general purpose compute, it means that any compute element, which is a CPU, the core, which actually performs an instruction set, and which operates on data. So a general purpose compute can be generalized in terms of any CPU, DSP, Tensilica, embedded CPUs, client devices, Qualcomm Snapdragon for your cell phones, and then at the higher end, Intel Atom CPUs, ARM, and AMD's Xeon, Intel Xeons. So all of these wide array of CPUs are all the part of a general purpose compute, where any software can be run on them, provided we have compiled that application, particularly for the desired architecture. So, if it is CISC architecture or RISC architecture, to in whatever instruction that the CPU understands, then if as long as the application is compiled to that specific compute node, we will be able to utilize the compute properties of the CPU. So to understand what is general purpose CPU, general purpose compute. It's all the CPU collection of all the CPUs that can be programmable, and it may include RISC or CISC architecture, and it can maybe hybrid. It can go to as small as client devices and as large as server, big servers on CPUs. So if I were to write, general purpose compute, let's drag draw, and then let's just say this as a CPU, and this CPU could be RISC or CISC. RISC example is ARM architectures. CISC could be Intel and AMD. So the deployment consideration of this would be, there will be a platform, there would be a CPU, there is RAM, disk, all other IO inputs, and then NIC, packets will come in, and then we have a OS layer on top of this, and then we get to use, applications will be able to interact with this hardware. So packets come in, and then it goes to application, it computes here, and then comes back and goes out. So that's how it's our general purpose compute, which is like CPU, can be programmed to perform this task. So when we do this, what would happen is it generates a lot of a high amount of activity in the platform. When we refer to a platform, it's fundamentally the hardware. For example, purpose compute, it could be a server chassis, client device, such as your mobile phones, or laptops, and any other compute device that you can think of. And now what we're trying to do is we take the general purpose compute, and then we are programming it to process the packets. Right? So the characteristics of what would happen when we run when we were to run such um, a traditional packet processing, which is like switches, how they process packets. We take the functionality and try to implement that function on a general purpose CPU. What would happen when we do that? When we, in terms of hardware, we have characterized the properties that where hardware would find things in terms of critical aspects. Where like if we were to run a packet processing workload on a general CPU, what are the things that would get impacted, or I would say how the characteristics would change. So one is IO intensive. What does IO intensive mean? So IO intensive mean that there's a lot of input output operations that are happening, because the packet processing event itself is an IO, where the packet will be arriving on the NIC, and then it traverses through the interconnects, and then it goes to CPU, it goes to memory, it gets it gets computed, and then traverses back, and then do the transmission over the NIC again. So the IO aspect is very high. So it's IO intensive. So it depends on the traffic rate. If the traffic is too high, then it's going to generate an intense amount of IO activity. And then there is compute. Suppose, let's say that packet needs to be inspected. For instance, we can say the deep packet inspection. We need to do traffic analysis, and then we need to, let's say, encrypt, decrypt, compression, decompression. All these tasks are compute intensive, and those needs to be performed for every individual packet. So if there is a very high data rate, so every packet needs to be performed with a high compute, and that would impact the CPU operations. So if you were to run any other application on the GPU, on the GPC, the network compute, and along with your network function application, your network function would take in high amount of compute resources. And also data is sensitive, in a sense. um, the characterization of packet processing inside the compute node hasn't been deterministic. The package traverses the how package traverses through the internal interconnects and memory of a platform. So once it arrives onto a system, how system propagates this packet identity internally over different um, processing components and interconnects, just PCIe, USB, and then on-chip fabric, off-chip chip-to-chip fabric. So all of these components are non-deterministic. So they have buffering, arbitration, they have QoS internally. So the total amount of processing time depends on a lot of factors, and not only the processing time that it takes for the packet to get computed. And then there is another part is that it's repeated and routine, which says that the action on every packet is nearly the same for all the packets. So that's repeated and it's routine. So the packets are arriving and you have to compute over and over and over again. And we need dedicated capacity in order to support dedicated traffic. So suppose if you were to say my network function application is an application. So the network function is supporting 1 gigabit per second traffic, then you have to allocate dedicated capacity and the resources to be able to maintain the data rate that is required of 1 gigabit per second. The large memory. So the large memory is required for storage and buffer, because the line rate, the data is coming at a huge amount, and if we were to buffer data of 10 seconds, we need like nearly 10 GB of data. And if you do network slicing, and if there are like large number of flows requiring bigger buffer sizes, then naturally the total amount of memory required by the device for network application increases. So with all these approaches, there is also what we are looking at. The network function characteristics is purely from hardware perspective, but from a software perspective, what would happen is the OS takes care of management of resources for applications. That's the primary purpose of OS. But the original inception of OS was not to perform packet processing. It was for task allocation, it was for isolation between the task, and also for resource sharing. So now the principles of OS doesn't necessarily match with the principles or the characteristics for the packet processing. Since there is a there's a big differentiation. What we would there's a big Since there's a big differentiation, there is a scope for optimization to bring these two requirements and the principles of OS to as close as possible, and then to improve the efficiency of the network function execution on a general purpose computer, on not only general purpose hardware but also general purpose software. General purpose software is a normal operating system. So if we were to look at some of the items here is, we need thread and process scheduling, then we would need a memory management, we would need interconnect management. So this comes under hardware, this comes under hardware, and this would be software optimization. Dynamic frequency and water scaling is to adjust the frequency of the CPU and then the voltage level of the CPU, such that we can voltage level is for power saving, frequency is also power saving. So we depending on whether we need at a given instant, if we were to overshoot performance with high voltage and high frequency just to accommodate the burst of the traffic, things like that. And then the core pinning, so an application would be core pinning is a fact is a technique in which an application can be fixed to run given um, on a given CPU, right? And then there is cache. We can allocate the cache. Um, the property of cache is to reduce the latency of memory access. So cache is a very important factor in network function implementation. And then the IO management. So IO management is a very important aspect, because whenever the packet arrives to a device, which is, it can be modem, it can be modem for the cellular modem, let's say, or the NIC, network interface card, um, where your packets will be stored in internal memory, and then the CPU would go and poll it and pick up if there is a data, or if it could be the interrupt mode, where whenever there is a data we go and interrupt the CPU. So there are different mechanisms, and each one has their positives and negatives. For instance, if it is interrupt, so it is what we are discussing right now. If it's an interrupt mode, there is an interrupt latency. There is a context switches. So there is a lot of inefficiency in the interrupt. The polling, however, would continuously poll for the data, and as soon as there is a data immediately the software is going to go pull the data in and then process back it. So, but it's faster, but it takes a lot of resources because polling would continuously poll, and the wasted polls are, are actually power. It's not power efficient and it's not compute efficient. So the next topic that we will be discussing is how to improve in terms of hardware. So in terms of software, there are some strategies that are applied to focus on the transparent moving of packets from one location to another location within the hardware. But the acceleration component is from the hardware perspective, how efficiently we can utilize the available hardware, and if we cannot, how we can utilize the auxiliary compute element, accelerator CPU, how we can utilize them in order to get the achieve benefits and also have the highest performance for the NF on a given hardware platform. So there are various different forms of compute. One is CPU. CPU is the most generalized form where we can program the CPU, we can write a code, and it will execute. So that's one form of compute. And then there is GPU, which is graphic processing unit. So inherently the sorry, so inherently the GPU is highly parallel, which there is a tiny functional units in the GPU, which is highly efficient when performing floating-point operations, and there are like thousands of cores on a given GPU, which is able to perform thousands of independent operations. Similarly, the FPGA is a programmable logic. In contrast to GPU, the GPU can be coded. We can compile the code and then we can run immediately. But in FPGA, if it were to require a logic, design of a logic for complex math operations, and then it performs nearly efficient most complex operations in the most efficient way in terms of power and time. FPGA is still reconfigurable, it's still programmable, but at a higher degree than GPU. And then there's the ASIC compute where there is no option for us to program, where the functions of the compute are burned into silicon, and then we just pass in the set of inputs, and then it would be able to give us a set of outputs. So ASIC is one of the most efficient, power efficient, and then compute efficient way of implementation of acceleration. The term acceleration is actually is referring to the main network function is able to be accelerated by this additional component in addition to CPU. So if an application, a network function application is able to run natively on the CPU, that's the baseline. And if we were to add a hardware component, an extra additional hardware component to be able to make this network function to run faster or to have more power efficient way of compute. So if we were to optimize it in any form of the network function through an hardware, we could refer that phenomenon as an acceleration. Right? So what would happen in this scenario is now we have multiple options. Now we have CPU, which is software version, the GPU, FPGA, and ASIC. There are multiple options, and which one to choose, right? So typically, nothing fits. No one size fits all. So we have to now devise an optimal algorithms and principles to figure out which task should be run on which of these acceleration component. So it's not that the entire function is either run on the CPU, GPU, or FPGA. If we were to take an example, let's say this is a complete form of network function, then we would take these tiny parts and then we could move these into different accelerators. So the bigger part, all the leftover ingredient part, this CPU, this So basically basic screen for example. This is a bigger task. So basically the reference of is taking a task and then it is generating task pool and it would schedule in homogeneous across multiple processors and multiple computer. That's ideal. This is what ideally we would need, but we are getting there. There is a lot of research work necessary in terms of how to split the task and what needs to be uploaded, what is the upload cost, and things like that. Right? So the additional thing that needs to be understood here is how the softwareization of a function works in the bigger ecosystem and tools and resources that are available in existence. Right? So we have this hardware platform. So a hardware platform would have the smart NICs, FPGAs, GPUs, which could be all these three combined could be a custom accelerator, custom license. We can program it the way we want at a given time. That's a custom. And dedicated accelerators, on the other hand, what they would do is they would implement this function uh, on a fixed basis, and in the sense these accelerators would have inherent compute and which will only be dynamically using. There is no programming capability here. This and we just go and use them. Then resource data technology which will able to allocate the resource, do the resource slicing and everything. In terms of storage, we have NAND technology which is faster than disks and but is slower than the RAM. So we have the DDR, memory with persistence memory, with the NV NAND is an advancement. So we have a very advanced hardware capabilities, and then we have OS, right? And this OS will implement strategies such as kernel bypass, application direct access to hardware. Things like compute components are GPU and CPU. So some aspects of FPGA as well. Um, so on top of this hardware, we will have an operating system which which traditionally hosts application, and then there is a special kind of operating system which is also called as hypervisor. So what this would do is fundamentally uh, provides the resource slicing and also isolation between the virtual um, entities that it hosts. So what hypervisor would do is it hosts the guest operating systems. So the traditionally hypervisors are also called as virtual machine monitor and are the host OS, and the virtual machine that it hosts is called as guest operating system. So in the virtual machine, inside the virtual machine, we can host specific applications for performing network functions. And then in the additional layer to the OS and hypervisors is the container engine. So what this container engine will do is it hosts the containers and network functions which are implemented as containers. So here we can observe the multiple different forms of network functions. One is bare metal network functions, which is here on the left side. Bare metal network functions directly operate on the hardware with definitely with the help of um, operating systems. And there is virtual network functions, which are also called as virtualized network functions. And the phenomenon of virtualizing network functions is called as network function virtualization, which we have heard in FE. And then containerized network functions. So there are these are the different forms of network functions. So with this overview of softwareization network function, um, I want to conclude the discussions on software-defined networking and software-defined network functions. So in summary, softwareizations of network functions are helpful for flexibility and also to enhance and scale the network functions. They are no longer static entities. These are now softwares which can be upgraded, manipulated, modified, scaled, copied, moved. So all the benefits of software development comes along with the applications for network functions. So with this, I hope we have at least a fundamental understanding of what is network function and how SDN helps to instantiate network functions, how it is maintained, what kinds of hardware that exists, and what are the different optimizations that can go into the future designs of network functions. So thank you very much for the opportunity on this presentation. Really enjoyed discussing with you all. So I hope to receive some comments and questions. Please write to me, and thank you again.